Okay, um, we'll try to dismiss a little early today if we can. By the way, there was, for this class only, section 2, the noon lecture section, there was a set of bloopers on the answer key. And so the everybody's exams had to be regraded. We have printouts for them, new printouts. So your old printouts you can keep, um, and I'm going to have to do new blurb sheets and everything for you guys. In case you were wondering about the blurb sheets, they're held up by this. So we regraded everything Friday, and we just got the printouts back. And so you may notice your grade. Hopefully, it goes up a little bit. Maybe not. And a student who came to office hours to go over the exam with me was the one that spotted it and brought it to my attention. So that's always a good thing to do. And speaking of office hours, Miss Darian did have some office hours yesterday, 1 to 2 p.m., correct? Yeah. And so there she is, an action photo. And that's what she will look like if you go and meet her in the atrium right next door in the physical sciences building, Mondays. And as I say to you, I say to all, that studying with another human being is very helpful for you, because on exams, in my class anyway, you have to really think. You know that my exams, they are not cinchy. They're not a walk in the park. There's basic questions on there, yes, but there's some questions that really make you stop and read carefully and think carefully, and to make that more efficient and more accurate on exam day for you, I recommend finding at the minimum a study partner from either this class or the morning class. Everything's working good. It's running good. As the display guy. At the minimum, find a study partner from this class or the other class. Study group even better, and talk things over at least once a week. Go to SI. That's another form of interaction with your peers and also with Shy, who has navigated this class from your perspective, and fruitfully so. And she got an A. And Darian, she got an A. Same year that Shy went through, same semester. So office hours with Darian, very productive. They say that lecturing is the least productive thing, the least productive mode of learning for students. And yet it's the thing that we do the most of here at the university, everywhere. Every university, pretty much. And it's the thing we do the most of. So every hour, every minute that you can spend with me, Darian, Shy, your study group, your study partner, or some of you may have a friendly physics major or a friendly engineering major that's not too annoying, that you can go to for tips. And that's, like your big brother or your little sister or something, whatever it happens to be. That's also good, another way to do it. So I highly encourage that for everyone. And now since we can't give a lecture in Elvish, we're going to give a lecture in English concerning momentum and impulse. Because if you like the Lord of the Rings trilogy, which I happen to like, I don't know, I've read that trilogy about, I think, 4 times in my life now. I really like it a lot. But unfortunately I cannot speak Elvish like, all those guys. I'm more like Samwise than anything else. Anyways, here's the momentum impulse formula. F delta T equals delta P. We're going to use that, and let me remind you that it looks like it's not F equals ma, but it's actually just another version of Newton's second law, F equals ma. And even the guys in the engineering department that have F equals ma engraved in their brain permanently and for life would recognize this as just a variation of Newton's second law. And it's a way that you can recast Newton's second law into the language of momentum. It's perfectly kosher. Now, what I want to do with you is reinforce an example. So get thy clicker. Forsooth. And hearken ye to your clicker. And you better get your calculator out too. Cell phone. Now, all right. So we're ready to go. And what we're going to do is compute the impulse on a basketball in free fall. And we have a large scale motive for this. It's going to lead us to the idea of conservation of momentum. And but for now, we're going to just do a computation of impulse. And the time interval that we're going to use is just a good old, easy to work with 0.25 seconds, quarter of a second. No particular reason, just wanted a nice round number to work with, and that's what we're going to work with. So that'll be our delta t. And we're going to work with an NBA basketball. And so because of that, we're going to work at a few specs first for the weight force and stuff like that. So that's your clicker question. So get your clicker ready. And if you haven't used your clicker yet for the first time, hold the power button down till you get the flashing square. Then type in the letters B and B again, and that'll sync you up with the session. Forsooth. Question 1, multiple choice. NBA basketball, the mass is 0.62 kilograms. What is its weight force? D D D D D D D D D D D D. This should be easy. Dun 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 dun. This should be a walk in the P-A-R-K, park. Hopefully. I had a student come up to me after the morning lecture, and she said, Dr. B, are we going to be doing all new stuff for exam 2? I mean, this is new stuff, is it? I said, we're going to be talking about F equals ma the rest of the semester. It's never going to go away. Free fall, we're going to talk about it a lot. So, 20 seconds. So this should be, by the end of the semester, hopefully this will be an easy calculation for you to do. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for here. This is interesting. This is very similar to the morning lecture. A lot of you voted for A. That is incorrect. The correct answer is C. And we're going to go with 6.08 for our actual calculation that we use. I don't know, 0.155. I think maybe that's the distance. But the suffix here, the unit suffix is Newton, so that wouldn't make sense. Anyways, if you got that one wrong, make a note that this is the correct answer. And I want everybody to jot down all 4 of those options quickly, because I'm going to ask you a mental IQ test question now about test-taking strategy. In other words, all right, this is multiple choice, and let's say that you don't know the answer. Can you eliminate some of the other options? So the question is, why or how can you eliminate those other 3 options? Now, I'd like you to talk that over with your neighbor, because you're going to have a clicker question. to type in your answer to this. So talk it over with your neighbor. How can you eliminate um, options A, B, and D? Why? No, I see your. I don't want you to answer the question. You're going to type it in on your clicker in just a second. So just talk it over with your neighbor. See if they agree. If they don't, talk it over and. Okay. A, B, and D are incorrect. And on a test, you want to be able to eliminate those, at least one of them, if you can, if not all three. And the question is, on what basis do you eliminate them? So, it's a good question. Now, I want you to hit your refresh key on your calculator, and because we're going to do a code question. Here it is. Use this code table. And type in your answer. So, for instance, TBOP, velocity is always smaller. Now, don't type that in because that's not a good answer. But form your own answer and see what you can see. Question in the back. W equals mg, man. The weight force. That should be an automatic pilot, autopilot. Yes, a bunch of you voted for A. But it's the weight force that's one of the specs you need. If you want to figure out an impulse, you need to figure out the net force that produces the impulse. In this case, basketball and free fall, it's the weight force. Okay, click in your questions, figure it out and answer, talk it over. Or not. And then hit the send key. Don't forget to hit the send key. I can hear clicking, clicking, clicking. Very nice. Very, very good. And write in your answer also in your notes as well. And we will talk about some of the answers, some of the top answers. Be interesting to see what you guys answer. One minute. Hey, Darian. You guys ready? 15 seconds. Get your answer in. Question. What? Delta P? How do you? We're gonna do that. We're on our way. We're working through all this stuff. We're working through step by step so that you can get to delta P. We'll have it in just a second. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got. Here's the set of answers. The top answer is ABPU. Other options are smaller mass. Actually, that is, you can think of it that way. Those are the weights of a smaller mass. Yeah, that would be kosher. Next one, ABPC. Other options are P, smaller than correct option. I'm not laughing. Why are you laughing? There's nothing. That's legitimate. If you know the, see, because what you write and what I write for this might be completely different, but equally kosher. So that may be a kosher way of saying, I know what the size of the weight force is, and those are too small. See, because that's the correct way to think about it. Think about it this way, the weight force is always about 10 times whatever the mass is in the metric system, because G is pretty close to 10. So if you take the mass and multiply it by 10, okay, that's going to be close to your weight force. And there's only one number up there on that question that was close to 6. All right? The other ones were way too small. So this ABPC is not bad. Whoa, there's another one here. Number 3, 11 students chose this, 6% of class. It's a big, long one. I better bring this back over here. GBOQU. Let's see if we can decipher that one. GB, weight is OQU. Always larger mass. I don't savvy that. Next one. So I'd have to rate that one as incorrect. A, B, and C. Other options are and C. Never correct. Well, that's kind of circular reasoning, and so don't laugh. I mean, it's a legitimate thing to be on your guard against. You don't want to do circular reasoning. In other words, to say, if I ask you why are those options, why can you eliminate those options, you can't say, well, because they're wrong. I mean, you can say that, but it's only if it implies that you do know the correct answer. All right, let me go down the list here, see if I can pick something that's a little bit less popular. All right, here's somebody. I just went down at random here. All right, here's a bunch of single answers. Only one person typed in DEFPG. Let's see what that is. Of, equal, or, smaller weight. All right, that's similar to the one I was talking about a few minutes ago. If you kind of know the ballpark you're going to be in, those other ones are smaller weights for smaller masses. All right, so this is good. All right, hit the refresh key. We got more questions coming. You ain't done yet. You ain't even close to being done yet. Hit the refresh key because now you have a calculation. Here we go. How far does it fall in 0.25 seconds if it starts from rest? In other words, you're dropping it off the top of the library. How far does it fall? This goes back 2 or 3 weeks. Oh, I see pages flicking back and forth. All right. 1/2 GT squared today. If you use 1/2 GT squared, you can calculate the answer. Actually, Jeopardy, they're supposed to figure out the question, right? They get the answer, you got to figure out the question. That would be impossible for a numeric question. You know, like 1.52. Okay, what's the question? It's interesting if you think about it that way. You know, those Jeopardy answers have a huge amount of information relative to 1.52. So you analyze the information in the answer and back up to get the question. But you can't do it without a lot of information. And just giving 1.52 is not enough information. That's interesting. But it's enough information for these guys. 30 seconds. Boy, I just saw a student look at her neighbor with a very dubious look. Like, are you serious? 15 seconds. Get your answer in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. See, what we're doing here is we're getting the weight force. You need that for F delta T. The drop distance, you might need that for something else. So you may as well get these specs squared away. So we're just doing a few preliminaries. Okay, let's see what you guys have got. Whoa, we got a lot of geniuses in here, 0.31. And a bunch of you typed in 0.306. That's close enough for government work. I see some of you typed in the wrong answer. I'm not going to show you the answer, but some of you have the right answer for a different question. So, let's try another question. Hit the refresh key one more time. And let's do another drop distance. 1/2 GT squared. I was singing it. I sang it to you twice. No, it's just drop distance. You're dropping it from the top of the library. How far does it drop? 1/2 GT squared. Okay, hit your refresh key again. Multiple choice. All right, 0.5 seconds. How far does it fall in 0.5 seconds? Did you get it squared away? All right. Were they there? Was there somebody there? Oh, I should have told you to go down to the health services right down. Sorry. All right. We're clicking, so get your clicker ready. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 178 answers. Very good. Let's see what you guys have got. Ding, 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 ding. Very good. You guys got it. That's correct. Very good. 1.23 meters. And as I mentioned a few minutes ago, a bunch of you typed that in for the previous question. So be careful with that. You know, sometimes you have the right number for a different calculation. So you got to be careful with that. Now, if I was to draw this to scale, which the previous pictures were, this one would look about like that. Okay, so you can go ahead and sketch that in if you want. And now we're going to get to the main attraction. We're going to actually compute the impulse. So let's get back to our task. We'll now compute the impulse. We have the weight force. We have delta t. Delta t is 0.25, and that's our accounting increment. We're taking a look at the momentum every 0.25 seconds. I just made it up. I just chose a round number every quarter of a second. Our spec sheet says that the weight force is 6.08. Let's go ahead and use that for the weight force. And now we use F delta T for computing delta P. And this is multiple choice. Go to it. Gehen Sie zu. That was a little bit of German for move. Get going. F delta T, oh F delta T, I long to calculate you. Any spiders over there today? No? Good. That was bad the other day. I thought it was something bad over there instead of just a little spider. Well, actually, spiders can give you a bad bite. 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Did you get a click in? Did you click? Good. All right. Let's see what you guys have got. Geniuses. Good. Now, if you want to see how that calculates out, here we go. Here's my spec sheet up here in the, my cursor. I can't even see my cursor. I have no idea where my cursor is. Oh, here it is. I got a little tiny cursor. Here it is. Okay, here's your spec sheet up here. You use delta P equals F delta T, and just plug in your force, the weight force, 6.08 kilogram meters per second squared. Hey, you guys, that is a Newton. And normally I just write for a force, I'll write in the capital N to stand for newtons. But in this case, I'm typing it in as a quotient of fundamental units, kilograms, meters, and seconds, because the seconds in the numerator over here in delta T cancels with the seconds in the denominator of the Newton. So, all right, yeah, it's a Newton But if I write it out in fundamental units like this, Sarah, then you can see stuff to cancel. And so sometimes that's nice to, you know, it's a nice tool to have in your tool belt. A good strategy, because then you know the answer is going to be kilogram meters per second. All right, that's a momentum, MV, kilograms times the speed, meters per second. All right, in this case, it works out to 1.52 kilogram meters per second. And there is no fancy name for kilogram meter per second. Momentum doesn't, it wasn't named after anybody. Nobody yet. I mean, maybe it could be named after you. Or you guys in the back row that have your nose in your phone, maybe you become famous as a scientist. Who knows? It could happen. Yeah, I'm talking. Yeah, no, I'm talking. Yeah, you. Yeah, with a red phone. Yeah, yeah. She's not even looking at. Yeah, yeah. I was just saying it could be named after somebody. You never know. But right now it's not. All right, final note, and that is basically that these sketches, which we're going to redo in a few minutes, they were all done very carefully to scale. A basketball has a diameter of about 9 inches, and the distances vertically were all in proportion. That is true. If you did take a photograph of a falling basketball after a quarter second, it would look just like that. Okay, if you dropped it from the top of the library. All right, now let me pause for questions before we continue with our next main topic. You're not in trouble. It's all right. Everything's all right. All right, let's keep going. I want to think about strobe photos. Oh, question. Yeah.
Do you want us to find the weight force first and then do it? Because the calculator's going to be off slightly when we do that. So if it's like a quick question.
Yeah. I would do it. I would do the weight force, keep all the digits, and then round off at the last step. Yeah. So that's usually what I do. And I usually on a clicker. The question was, do you want us to do the weight force first, or wait until the very end to round off? And on a test. And what I normally do is wait till the very end to round off. And when I look at the answers for something like that, they're going to be in a spreadsheet from from clicking. And so I can easily sort them, and I'll be able to tell somebody that's off by a tenth or a hundredth, and I'll be able to give them full points or not. So, and I have done that. Some of you may have noticed that your exam 2 clicker score, some of you may have had 1 point. That means I gave you 1 partial credit point, probably on question 1, possibly on question 2. All right. If you got 4 points, definitely you got partial credit somewhere. And I like to do that. It's nice to be able to do that. You can't do it on Scantrons, but you can on clicking. All right, strobe photos. This is a strobe, I don't know, it's about a tenth of a second between flashes. Strobe is basically a flashing light with very precise pulses of light, very short, very bright, and you can usually either vary the timing according to the circuit, or you can have a set timing for the strobe. But usually it's very short time, and it allows you to capture motion, like this dove being released from this lady's hands and flying off to the upper right. You catch a couple strokes of the flight, the backstroke and then the forward stroke, and then you're kind of going out of the picture. Here's another one. Here's a drip coming out of a faucet. And these are all from MIT. They have a high-speed photography lab, very famous since before World War II. And if you like these cool kind of interesting photos, just type in Google Strobe and MIT, and just start looking at images. There's a lot of really cool images of, like, there's a famous one of a bullet. They caught a bullet going through an apple, and it's just everything is frozen in time because they had a really high speed strobe to capture that exact moment. They must have gone through a lot of apples before they got it exactly right, but it's kind of cool. And this is kind of a cool one too. Anyways, MIT and strobe, and just look at them. The guy up there, his name is Harold Edgerton. He is now passed away, but he was for many years was in charge of the high-speed photography lab, and they used it for a lot of scientific measurements and stuff. I mean, it generates a lot of cool pictures. So they're cool to look at, but also they analyze the you-know-what out of them because they're trying to figure out fluids like this, complex things like flight, from the previous image. So now I want to use strobe images and think stroboscopically about a vertical path, for which we've set up increments of delta t equal increments of time, delta t. In our example, we used 0.25 seconds. But Caitlin, we could use any time interval that we want. Free fall is pretty easy. We could have gone a tenth of a second, but 0.25 seconds, quarter of a second, works out really nicely. Now, if you take that vertical path as we did and divide it up into equal increments of time, i.e. kind of like a strobe photograph, then you get an image like this. Now, this is another very careful scale drawing. This is half size of the previous images, but I took a lot of time this morning to put those images of basketball right exactly where I wanted them. And that reflects accurately if we did have a strobe photograph of a falling basketball for the first half second, it would, with strobe flashes every 0.25 seconds, that's what it would look like. When you divide up the path in this manner using temporal accounting, your accounting goes by time, equal increments of time, temporal accounting. Then you get equal increments of delta p. Your momentum increases equally for every equal interval of time. So for every 0.25 seconds, we get another 1.52 kilogram meter per second of momentum in this example. Right now, if you have some other object, if you're dropping a paper clip, you get a lot less momentum. But if you did it every 0.25 seconds, what you get would be the same every 0.25 seconds, all the way down till it hits the floor. And you may think to yourself, well, Dr. B, this is kind of boring. Yeah, not really. But we're going to make it more interesting on Thursday. But before we drop off this strobe thing, the strobe concept, and come back to it Thursday, I want to mention a couple other things to you. And the first is that the increments of distance are not equal. And that's why I mapped it out carefully for the entire lecture. I wanted to make sure that I knew that I was going to be making this point. The delta y increments are not equal. They vary. They're getting bigger and bigger. It's speeding up as it goes down. So every quarter of a second, it covers more ground. Average speed is increasing. Right? So those increments, the spatial increments, no. Temporal increments, delta t, yes. If those are equal, delta p is equal. All right. Last point is that horizontally, there's no net force. So in the horizontal domain, delta p is 0. And just as Galileo analyzed the motion of a projectile, a cannonball, into horizontal and vertical components and figured out the straight up and down motion and figured out the horizontal motion. They kind of put them together mathematically. In a similar way, we can do that accounting horizontally with changes in the momentum. And momentum has three components, just as position does. Momentum can have an x component, px, a y component, py, so that would be the vertical component, and a z component, pz, coming out towards you or back away from you, okay? And then x going, left and right. So p has spatial components just like a velocity does because it's made from a velocity. All right. Now, I want to amplify on number 5. We're going to do an example together, Akin, that is going to work out the implications of delta p equals 0. We just did, free fall, okay? 1.52, 1.52, 1.52 kilogram meters per second for every quarter second of free fall. Nice, good. Now let's do horizontal. And what we're going to do is a horizontally moving system out in a freight yard, boxcars. And this one is going to be absent external net forces. All right, so we're going to take a set of boxcars, and they'll be able to hook up together. And the way boxcars do, they latch together and then they head off for Kansas City or wherever they're going. But no net external forces. Now let me ask you a question. And this is, I don't have a clicker question for it, so if you want to raise your hand and be bold and think, let me ask you this. You view a Northern Pacific boxcar like this one. This is one of the transcontinental railroads. Northern Pacific Railroad, all the way across Montana, the High Line. You observe the boxcar at rest. You're in the freight yard. When I was just out of college, I did a lot of traveling. I've never told the students this, but when I got out of college, I was out west. I was in Montana actually, and I stood around all day in a freight yard waiting to ride a freight train, which I did with a couple other guys, and I didn't like it that much. So I rode about 25 miles and I got off. But it was kind of an adventure. Anyway, so you're sitting around a hot day in the freight yard, waiting for the train to get rolling. You're looking at these, and they're putting together strings of, freight cars, box cars, and whatnot. And you're looking at this one, and it's at rest. Does that mean that there is no force acting on it? No? You say no? Who said? Dante? You say yes, there are external forces acting on it? So you're saying there's downward gravity force on it? All right, so how come it's not accelerating downward? So it's on the ground. So what does the ground do? The ground has got that rigidity force because they don't build freight yards where the ground is made of water. It's got to be solid. They don't build a freight yard where it's made of jello. It's solid ground, terra firma. And that rigidity force points upward, directly equal but opposite direction to the weight force. Good. And so you're looking at this boxcar. There are external forces, but the net external force is goose egg, 0. Because the rigidity force upward balances the downward weight force. All right. Now, on a good steel track, good steel wheels, the horizontal forces of friction are going to be really small, so we'll idealize it and consider it to be 0. Now, here's the case that we're going to look at in detail. All right, now sketch this out carefully because we're going to do a calculation in a few minutes with your clicker. One more clicker question. So don't let go. We're almost there. You still want to dismiss early? No? I saw somebody that didn't even go like this. They're just looking at me. Like, bored. Boring. Okay, you can stay in class if you want. All right, so we're looking at 4 box cars. And they're each 35,000 kilograms. So they're identical box cars. 35 metric tons. And we're going to say that the initial state is that, one of them moves in at 4.4 meters per second, V1. That's boxcar number 1. And then the group of 3 over there to the right side, is at rest. There's 0, and so that's V subscript G. The velocity of the group of 3 is 0. They're just sitting there. They're at rest. Okay, but the other one's coming in with 4.4 meters per second. So that's about, 9 or 10 miles an hour. It's kind of fast, actually, in a freight yard. They usually don't run that fast when they're switching cars around and stuff, but it's a good round number, 4.4 meters per second. Now, that's the initial state. Now, the final state is that they hook together, as freight trains do. Okay, that's why they bump that car number 1 into the string of 3. That's how they build up a string of freight cars, a big, long freight train. All right, so there are interaction forces where the 2 trains bump together. Okay, now let me ask you another IQ test question here. This one I don't have a clicker question for, but this, all right, this boxcar on the left, boxcar number 1, it's going to get an interaction force from the other 3 that are stuck together already. All right. Now, what direction is the interaction force going to be, left or right, on boxcar number 1? What do you think? To the left? That is correct. Okay, so interaction force on boxcar 1, you go ahead and make a note, is to the left. Therefore, its acceleration is going to be leftward, whatever size it is. It might not be very big, but it'll have an acceleration. It'll have a delta V. It's already moving to the right. It's getting an acceleration to the left, so that means it's speeding up or slowing down because of the interaction. Slowing down. So it's gonna have a little bit less speed. Now, the string of 3 the 3 box cars that are already strung together, what direction is the interaction force from boxcar 1? To the right. So they're going to get an acceleration to the right, and that means they started at rest. They're now going to be moving to the right. All right? And the way these things work, they're going to go off at 1 speed. All right? They're going to latch together. Okay? And so that's what we want to figure out. The final state, what is the new speed of this string of 4 freight cars? We know that there's some interaction forces, but those are interaction forces, so they don't change the delta P. Or I should say they don't change the momentum. Delta P is going to be 0 because those aren't considered external forces. It's kind of like if you jump out of an airplane and you're in free fall, you're experiencing a downward external force from gravity, but then if you want to take out your glasses and put them on, or take out a can of Pepsi and try to drink it, or, well, you wouldn't drink a can of Pepsi. What would you do if you're in free fall? Take out your cell phone and call Ma. Hey, Ma, look, those are all, you're using a little bit of force to do all that stuff, and zip your pocket, and, put your hands in your pocket. Whatever you're doing some force. But those are all interaction forces within you, part of you. Okay, those aren't external forces, but gravity is the external force, and that's the one that's accelerating. So the same thing here. These are interaction forces, not external forces. All right. So let's figure out this situation. First, let's calculate the total initial momentum, P subscript I. All right. It's figure out MV for all four objects. Now the first one is 35,000 kilograms right here in the first parentheses. P subscript I equals 35,000 kilograms times second parentheses 4.4 meters per second. Okay, that's the momentum of boxcar 1. Now the other three are stable. They're stationary. So those are zeros. Now you don't have to write those zeros in, but I did just so that you can see that, we have 3 boxcars in addition to number 1, but they contribute 0 to the momentum. So the total momentum, initially speaking, is 154,000 kilogram meters per second. Raise your hand if you verify that calculation. Get your calculators out and verify with me as we go. It's always a good thing to try to do as we go through the lecture. Now, since there's no net horizontal external forces, good steel rails, good steel wheels, balance of gravity and the rigidity force of the earth and the track, delta P is 0. And that means that PF, whatever else it is, also has to be 154,000 kilogram meters per second. So write down final momentum, P subscript F, equals 154,000 kilogram meters per second. And that, my wonderful students, is because there is no net horizontal force. There's no horizontal gravity. It's just, and there's a little bit of friction. But those rail cars, they will just keep going for miles. You get them going, and if it's a level track, they will just go for a long way before they slow down, even loaded. Now, by definition, that momentum, P subscript F, is also an MV. Now, the mass is the mass of 4 boxcars. Now, 4 times 35 is 2 times 70, so 140. So 4 times 35,000 is 140,000 kilograms. So that's the mass of my new object, my new string of train cars. And it's got a new speed, V new, V subscript new, N-E-W. All right. Now that's what we want to calculate. And because I have the definition, so go ahead and write down on the right-hand side here, that's from the definition of momentum. On the left-hand side, that's from delta P equals 0. So the left-hand side comes to us courtesy of Newton's second law and the impulse equation. And the right-hand side comes just from the straight definition, mv. Okay, if you know the mass and the v, you can always figure out mv, and that's what we're trying to do here. All right. So 154,000 kilogram meters per second is equal to 140,000 kilograms times v nu. So all we got to do now is divide both sides by 140,000. All right, so go ahead and do that on your calculator. Here it is. And hey, you guys, you can cancel kilograms top and bottom. Or if you go back up here to the equation above that, you can cancel kilograms left side and right side. Either way is good. And so you're left with meters per second, which is good because you're trying to figure out a speed. All right, and if you figure this out, you calculate it out, as you will do in the next clicker question, you get 1.1 meters per second. All right, anybody verify me on that? You got it? Okay, question. 140,000 is because we have 4 boxcars in one big locked up set, and each is 35,000 kilograms. So 4 times 35,000. All right. Now, students, this is an example of something that we call the conservation of momentum. The conservation of momentum um, means that if there's no external forces, the momentum before and after will be the same. We saw that in another really nice example, the skateboarders, when they were up here on the stage. And we worked out all their velocities and stuff. And the same with Bob and Carl in the textbook. Now, here's a good way of, in an English sentence, not an equation, but an English sentence, of stating the concept of conservation of momentum. The total momentum of a group of interacting objects remains the same in the absence of external forces. And you know what, you guys? You should write in there. This is my oversight. It should be in the absence of net external forces or unbalanced external forces. Okay, so, and here's another thing that you can put in there. Go ahead and circle the phrase remains the same. That means delta P equals 0. Okay, so that's a little equation for that part of the sentence. Now, I want to try this with another set of boxcars with you, and then we can dismiss. Now, here's your problem, and hit the refresh key, because we have a numeric question. You're going to do a calculation. And let's see if you can handle this. Same set of boxcars, but V1 is different now. Instead of 4.4, it's 6.4. A little bit faster. See if you can figure out your answer. And I'll give you a few minutes for that. So consult with your neighbor. Talk it over. If you have a neighbor. If nobody's sitting next to you, I guess you can't do that. I didn't dismiss anybody. I don't know why you guys are getting up. Busted. It's all right. We're almost done. 30 seconds. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Came late, just leaving early. Yeah, 1.6. You guys are geniuses. All right. Homework by supper time tonight, if not sooner. You are dismissed 6 minutes early. Yes. And you can come up and get your printout if you didn't already get it. Hey, you want me to? Can I give this to you on Thursday? Yes. Perf. Dare has the printouts.